Welcome viewers to the second segment of the first lecture for the course of linear algebra. We start this segment by showing how to write a system of linear equations using matrices. Let me write a system of linear equations. We focus on the following system of linear equations. A11 x1 plus a12 x2 all the way up to a1n xn. Okay, this is the first equation. We set it to b1. Okay, so there are n unknowns, x1 x2 all the way up to xn. These are the unknowns. The second equation is a21 x1 a22 x2 plus all the way up to a2n xn, which is equal to b2. The mth linear equation is given by m1 x1 plus a m2 x2 plus all the way up to amn xn. We set it to pn. Okay. So this is a system of m linear equations in n unknowns. Okay, m linear equations in n unknowns. And this system can be expressed in matrix notations, can be expressed using matrix notation as follows. A times x is equal to b. Okay, so I need space. Let me erase everything. So just now I have written out a matrix equation. Ax is equal to b. Here A is equal to aij, where I varies between 1 and m, and the column index varies between 1 and n, so that this guy is an m times n matrix. Okay, and there is a name for this matrix. It's called the coefficient matrix. The name suggests that the entries of this matrix are the coefficients of the corresponding system of linear equations. Okay. Remember that the first equation of the system was given by a11 x1 plus a12 x2 plus all the way up to a1n xn is equal to b1. Okay. So when I write the coefficient matrix, the first row is going to be A11, A12 all the way up to A1n. This is how I form the matrix of coefficients, or the coefficient matrix of the underlying system of linear equations. Okay, so we explained what is A, and now X is the column vector of the unknowns, and we know that there are n unknowns. So this is x1 all the way down to xn. Okay, so this is an n times 1 column vector, and B is the matrix of the corresponding constants appearing on the right side of the system of linear equations. So there are m rows in this column vector, b1 all the way up to bm, because there are exactly m constants there, right, associated with the m equations of the system, right, is an m times 1 column vector. Okay, it makes sense because the size of A is m times n, the size of x is n times 1, so we expect a matrix of size m times 1 out of this multiplication, and B is exactly the size of m times 1. So it is a well-defined matrix equation, right? Good. We give an example how we write system of linear equations using matrices. For example, the following system of two linear equations in three unknowns So we focus on this system. The first one being, the first equation of the system is minus x2 plus 2x3 is equal to 2. The second equation of the system is 3x1 plus 4x2 minus 6x3 is equal to 1. Okay, so the coefficient of x1 is 0 in the first equation. Okay, so you can rewrite it as 0 times x1 minus x2 plus 2x3 is equal to 2. Okay, so the matrix equation of this system reads 0, minus 1, 2, 3, 4, minus 6. Okay, this is the matrix of coefficients corresponding to this system, and there are three unknowns. I place 0 here because the coefficient of x1 is 0 in the first equation. Okay, so the column vector associated with the unknowns is x1, x2, x3, and the column vector containing the constants is just 2, 1. Okay, so this system of linear equations can be represented by this matrix equation. Okay, now we want to discuss various identities satisfied by the defined matrix operations. Various identities satisfied by matrix operations. Okay, So the first one is distributive laws. Distributive laws. Okay. A times B plus B prime is going to be A times B plus, A times B prime, and A plus A prime times B is equal to AB plus A prime B. Let us number this matrix equation as 1. And the associative law. The first one was distributive law, and this one is associative law, which reads as AB. First you multiply A with B and you get a matrix, and you multiply the resulting matrix with C, okay, and that has to be equal to A times the matrix that you get after multiplying B with C. Okay, this is what we call this is what we number by 2. Okay, two very important laws associated with matrix operations, and these laws will hold as long as the matrices involved are of suitable sizes so that the products are defined. Okay, see that there are addition of these two matrices here, so they have to be of the same size. There are multiplication of matrices here. Okay, so the column number of A should match with the row number of B. They have to be the same. The column number of A has to be the same as the row number of B prime, which actually follows from the fact that B and B prime are of the same size, which we demanded first. Similarly here, A and A prime have to be of the same size, and the column number of A or A prime has to be the same as the row number of B. Okay. Same things hold here, like the column number of A has to be the same as the row number of B, and the column number of B has to be the same as the row number of C, so that the associative law makes sense. Okay, good. Now we give an example of the associative law. Okay, for example, we have three matrices A, B, and C. See that the product is written by A, B, C because they are both the same. The same thing that we finally have is denoted by A, B, C, or you can write separately, like A is equal to this matrix, this 2 times 1 matrix 1 2. B is 1 0 1, this row vector which has 3 columns 1 0 1, and finally you have a 3 times 2 matrix 2 0 1 1 0 1. Okay, so first we compute A times B times C. Okay, we first multiply A with B and then multiply the resulting matrix with C. Okay, so when we multiply A with B, see that this is of size 2 times 1 and this is of size 1 times 3. So A times B is expected to be a matrix of size 2 times 3, right? So let us write this 2 times 3 matrix. The first entry is 1, then you have 0, then we have 1, you have 2, 0, 2. Okay, so this is the 2 times 3 matrix. Then you have the 3 times 2 matrix, 2, 0, 1, 1, 0, 1, and you do the multiplication to have what? 2 times 3 gets multiplied with 3 times 2 to have a 2 times 2 matrix, right? The final matrix will be a 2 times 2 matrix. So let's compute it. 1 gets multiplied with 2, 0 gets multiplied with 1, and 1 gets multiplied with 0. So the result is just 2, and this entry is going to be 1. This entry is going to be equal to 4, and this final entry is going to be equal to 2, right? 2, 1, 4, 2. This is what we get if we write the product this way. Now we are going to write the product in the other order, right? A times B times C. We multiply these two matrices first. So this is a 1 times 3 matrix and this is a 3 times 2 matrix. So the resulting matrix will be a 1 times 2 matrix, right? So the first entry is going to be equal to 1 gets multiplied with 2, 0 gets multiplied with 1, and 1 gets multiplied with 0 to result in simply 2. And the other entry is 1 gets multiplied with 0, 0 gets multiplied with 1, and 1 gets multiplied with 1, so simply 1. Okay, so this is a 2 times 1 matrix, and this is a 1 times 2 matrix. So what do you expect? You expect a 2 times 2 matrix, so there will be 4 entries. So the first entry is going to be 2 here, then you have 1 here, 1 gets multiplied with 1 and to result in 1. Then you have 4, and finally you have 2. You get that this matrix is the same as this matrix, which verifies that the associative law holds. Okay, good. Now scalar multiplication. So scalar multiplication is compatible with matrix multiplication. What do I mean by that? Let me erase everything here. Scalar multiplication is compatible with matrix multiplication in the following obvious way. In the following way. So there is a number C that you multiply with the multiplication of A and B. Okay. it is the same as having CA multiplied with B, which is again the same as A multiplied with CB, okay, where C is just a number. This is what we numbered by 3. Okay, now an important fact is that the commutativity or the commutativity law so the commutativity law means if you have well defined products of matrices, then AB is equal to BA, okay, but this generally does not hold for matrix multiplication. So this commutativity law does not hold in general for matrix multiplication. Which we already wrote here, that AB is not equal to BA. And you see that if A times B and B times A are both defined as long as the size of A is m times n, and size of B is n times m, then both A times B and B times A are defined, but they are not of the same size if m and n are unequal. Okay, so there is no question of equality of these two matrices. Okay, because they are not even of the same size, we cannot talk about their equality. So they are of the same size if and only if both A and B are square matrices of the same size, right? Like A is of size n times n, so is B, so that A times B is size n times n, and also B times A is of size n times n. Even then, we cannot talk about their equality. This is the thing. Matrix multiplication is non-commutative. Okay. All right. So 0 sub m times n denotes a zero matrix. By zero matrix, we mean that all the entries of this matrix are 0. Okay, and the size of this matrix is m times n. Okay, a zero matrix of size m times n. Okay, good. Now, a square matrix is a matrix of the row number same as the column number. Okay, in other words, the row number and the column number are the same for a square matrix. Okay, the square n times n matrix whose only non-zero entries are 1, in each diagonal position is called the n times n identity matrix. Okay, identity matrix, and is denoted by I sub n. Okay. Okay. So this is how you denote an n times n identity matrix. It has n number of rows and n number of columns, and all the off-diagonal entries are 0 and the diagonal entries are all 1. Okay, so that 1, 0 all the way up to 0, the nth entry of the first column. Similarly, I'm writing now the second row starts with a 0, 0, 1 all the way up to 0, the nth entry of the second row, and all the way up to the nth row, which starts with 0, and the last entry of the nth row is going to be 1. Okay, and you should be able to check that if E is an m times n matrix, then the following holds I sub m times A. You see that this is well defined, since I sub m is of size m times m and A is of size m times n. Okay, and this is going to be the same as A, which is of course of size m times n. Okay, and A times I sub n is going to be A as well. Okay, okay, good. So there are n number of rows here, and there are n columns here. Okay, good. Let me erase everything. Let A be a square matrix n times n matrix if there is a matrix B such that AB is equal to I sub n and BA is equal to I sub n. It will only make sense if B is of the same size, right? So I did not bother to write it. You should be able to understand it from the context. Then, if this is the case, then B is called the inverse of A and is denoted by A to the minus 1. But you don't call it A to the minus 1, you just call it inverse of A. Okay, so from 4, so we are just replacing B with A to the minus 1 or inverse of A. Nothing new. Inverse of A times A is I to the n, which is also the same as A times the inverse of A, which we call 4 prime. Okay. Okay, so this is the definition of the inverse of a matrix. If it's, if the inverse exists. When A has an inverse, it is said to be an invertible matrix. Okay. When A has an inverse, it is said to be an invertible matrix. Okay, good. So let me give you an example. So we are given a matrix A, 2, 1, 5, 3. Okay, it's a 2 times 2 matrix. Now we claim that this matrix is invertible with the inverse given by a 2 times matrix, 2 times 2 matrix, 3 minus 1 minus 5, 2. Okay. So let us check that the multiplication of these two matrices in any order is going to produce the 2 times 2 identity matrix. Okay. So 2, 1, 5, 3 multiplied with 3 minus 1 minus 5, 2 is going to be equal to 6 minus 5, 1, then minus 2 plus 2 is 0, then 15 minus 15 is 0, then minus 5 plus 6 is 1. Okay, we get the identity matrix. Now we put 3 minus 1 minus 5, 2 first, 3 minus 1 minus 5, 2 first, and then we put this matrix 2, 1, 5, 3 and do the multiplication to have 6 minus 5, 1, 3 minus 3, 0, and then minus 10 plus 10, 0, then minus 5 plus 6, 1 again. Okay, which means that A inverse is indeed an inverse of A. Now let us quickly check the fact that an inverse is unique if it exists at all. Okay, let me erase everything and check very quickly the uniqueness of the inverse if it exists. Let B and B prime be two matrices satisfying 4. Since I erased it, let me write 4. AB is equal to I sub n and BA is equal to I sub n, which was the definition of the inverse of a matrix, right? This was 4. So let us assume that there are two matrices B and B prime satisfying this equation. Okay. So we use this part of this equation 4, for B, so that we have AB is equal to I sub n. We don't use this part for B. Okay. And this part for B prime. Okay. B prime A is equal to I sub n. This is our equation number 5. Okay, now the associativity law, remember that A times B times C is the same as A times B times C. Okay, So by using this associativity law, one obtains that B prime times AB by using this law is going to be equal to B primes A, and then multiply the resulting matrix with B. But B prime A is equal to what? I sub n, right? According to 5. And here A times B is I sub n according to 5 as well. So this is B prime times I sub n, okay, which means that B prime has to be equal to B, which proves the uniqueness of the inverse. Okay, good. Now we take a break here. Thank you for attending the second segment of the first lecture for the course of linear algebra.